For the canonical ensemble, it's an ensemble in which temperature, volume, and the number of molecules is kept constant. And so this ensemble is useful for describing systems in which the temperature is manipulated. Of course, when it comes to experiment or it comes to many different other types of chemical systems, there are other variables that can be manipulated. For example, if pressure is the variable of interest, then rather than the canonical ensemble, it's actually more convenient to use what's known as the isobaric isothermal ensemble. And so here, in the isobaric isothermal ensemble, what's fixed is temperature, pressure, and the number of molecules, right? And so volume is allowed to change. And so now, the thermodynamic potential of interest is going to be U minus Ts plus PV, right? So now the thermodynamic potential of interest is going to be the Gibbs energy. Okay? And so I won't go through the full derivation of this, but I'll just kind of tell you the final important results. If we're trying to describe the probability distribution of this isobaric isothermal ensemble as a function of the internal energy and V, we would describe it like this. So we have our Boltzmann term in terms of energy. And now we add another sort of pseudo-Boltzmann term. Now it's a function of volume as well. And then all of that would be divided by some sort of partition function, which is going to be capital delta here. And I'll just call it the isobaric isothermal ensemble partition function. Okay? Where delta is just this. The summation of your Boltzmann term times your pressure term if you put these things together, what you find is that it's just the exponential of the Gibbs energy. Okay? Alright, so that's what it looks like in the discrete form. Of course, you could also write it in continuous form over some volume space like this. Alright. Alright, so this is what the isobaric isothermal ensemble, the partition function, looks like. Another useful ensemble, or another case to consider, is where, rather than pressure or temperature as a variable of interest, where instead, now the number of molecules, N, is a variable of interest. So this is useful for describing, adsorption, separations, or reactions. And so to describe this type of system, we use the grand canonical ensemble. Okay? And so here, we're going to be dealing with a system in which temperature, volume, and now the chemical potential are kept constant. So minus Ts minus mu n. And so this thermodynamic potential, it's kind of a different one. We're just going to refer to it as psi. So this is just the grand canonical ensemble thermodynamic potential. Okay? And so here, and then number of molecules, the probability distribution would be described by this. Mu n over kBt divided by its partition function, okay, where this partition function for the grand canonical ensemble is just the summation of the Boltzmann terms. Okay, and then simplifies into this negative psi kBt. All right, or in other words, you could write it like this. Your canonical ensemble partition function times mu n kBt. Okay? All right, so depending on the type of system you're trying to describe, that will determine what ensemble is the most convenient and most useful to use.